Hello, and welcome to another one of Ethan's engineering videos. Today we're going to be starting homework 2, which is kind of a big one. We're going to have 7 videos in total in this series. The first 3 are going to be a single chunk, which is going to deal a lot with probability, normality, and entropy, so kind of more a probabilistic take on events. And then the final 4 are going to be about finding the root of a function using some various methods, kind of figuring out which way is the best, and then expanding it from just a linear function to an array of as many independent and dependent variables as you'd like, and taking it from there. But obviously, you know the title of this video, so you're here to watch homework 2 part 1, so we're sticking with probability today. We're going to be really focusing in this specific video on the Central Limit Theorem. Forgot for a second what the last word was because I misspelled it, theorem, earlier. So I'll just write that out here. Central Limit Theorem. Make sure I spell it correctly. Theorem. And so obviously to cover that, we're going to need to know what the central limit theorem is, and then how we're going to actually show at least that it exists. We don't have to mathematically prove it yet. That's going to be topics of our second video mostly. So what the central limit theorem actually says is that as we increase the number of samples we take from a random data set, I'm using parentheses here so that you can actually see random. As we increase the number of samples we take from a random data set, they're going to approach a normal curve, which is also called a bell curve. And so what does it mean for something to be normal? And what does that have to do with entropy? And so the theory goes, and of course we're going to mathematically prove this in a bit, that because every single sample is randomly distributed, a single sample by itself could fall anywhere. And that doesn't really tell you very much. But when you aggregate them, and as you take more and more samples, we're going to find that the closer you are to the central tendency of the data set, the mean otherwise, the more likely you are to be for a specific sample to be found there. And obviously, as you start looking for samples that are farther and farther from that central tendency or mean, they're going to be less and less likely, and so there will be fewer of them. And so by taking many, many samples where each individual sample doesn't really tell you very much about the process you're drawing it from, as you aggregate that and take more and more, you're going to be able to define trends about your process that you're getting this data from. And so we're going to prove that numerically by just throwing a bunch of samples into a bar graph and seeing what sticks. So to get started, we're going to need to generate our data, and then we can plot it to show how the central tendency appears over time. So we're going to start by defining our new amount of data, because we're going to be using NP arrays for this. So we're going to need our number of rows, which we're just going to set equal to 10 for now, and we're going to need a number of columns, we're also going to set equal to 10. And from there, we can actually use that to generate a bunch of random data, and using those as the size of the matrix. So we're going to do, we're just going to call this data. And then we're going to generate it using, we don't have to say, it's just RNG, since we already defined NP, our random state. As you can saw, I brought in what we're going to import today because we're just importing the same old stuff. I think I'm going to be doing that from now on, to be honest, because we're importing the same old functions we go over in class. And it just saves me a couple of minutes and makes my life a little bit easier. And, I don't need to explain what numpy is every single time, every video. If I keep doing that, I'm probably going to lose my mind. So we're going to look at our RNG state, which we set up top, and we're going to call the random function. So we're going to just randomly pull a float, as you can see right here as the description says, between the intervals 0 and 1. So all we need to enter is the size of the array we're going to generate. Our size of our array is going, I don't even have to specify it technically since it's the only piece that you put into here, but the size is going to be n underscore rows by n underscore columns. So I run this, and we should be able to check here in our variable editor, which is another tool that I'm going to try to start using a bit more, that's since it was shown to me by my good friend Alec from Transport 1. And right here you can see we have an array that is 10 arrays, and each array contains 10 sets of numbers. But this isn't quite random enough for us. So I'm just going to do a little plus here and just do that right there. So now our data should be the same size, but it is now going to be between essentially 0 and 2, but most likely near 1. But that still isn't random enough for us. What we're going to do is we're going to take the average down our columns. So we're going to take every single row, and for each row, which is kind of its own array, we're going to take the mean of all of the data in that column, so that we will only end up with a single-dimensional matrix, or just at that point it would just be a list containing data points that are the mean of themselves 10 other data points. So we're going to just call this row averages, and that is going to be the np.mean, and we're going to take the array we're going to look at, which is going to be our data, and then what axis we want to add it down. So we know it's row is axis 0 and column, I did that backwards, row is axis 0 and column is axis 1. So we're going to multiply or do the average down our column, so we're going to axis to be equal to 1. And so now we let that run, and we see our row average is now going to be just 10 numbers long, which is, again, the number of rows we have. So that's what we expect, and that's good. So now that we have these averages, what do we do with that? So we have data points, but how do we actually turn that into a bar graph, since that's going to be the easiest way to actually observe our data's tendencies? So we're going to use kind of a new function here. It's going to be np.histogram, and this is going to generate, given our data again, so we're going to do row underscore averages. We're going to tell it how many bins we want to split that data into. And for convenience, we're just going to do 50 because we're going to be making a lot of data, and that just kind of sets our things nicely. And so given the data we have and the number of bins we want to split it into, it'll figure out, a good width for that and just kind of do all the background, not probabilistic, but graphing stuff that we need to do to get a set of both bins with the starting and ending index of those bins, those values, and then how many of each of our data points are in each of those bins so that we can plot them. So we're gonna spit that out as placement, as I said earlier. That's going to return how many of each of our data points are in any specific bin, and then obviously the location of our bins. So I'll run that, and there we go. So now all we need to do is we need to, having those bins, the location of our bins, and the placement of those bins, we're going to throw it in to Plotly. So we're going to create a new figure, and that's going to be equal to make underscore subplots. And then all we're going to do, I wanted to go to the next line, is we're going to do fig.add underscore bar. So instead of a big add scatter like we usually do, it's going to be add bar. And then our x is going to be equal to our bins, and our y is going to be equal to our placements. Because if you think about it, each of these bins, even though it's going to be a location, if we hover over bins here, we can see we have 51 numbers, which I'm not quite sure how it decomposes our bins exactly. But I guess that makes sense because we go from this number to this number, and then from this number to this number. So we have 50 spaces between each of these kind of start point, end point, and then this becomes the start point of the next one and the end point. So those are how our bins are arranged. And then our placement just tells us, okay, well, there's one piece of data in bin number, indexed like 15 to 16, and then there's 2 data points from bin number 30 to 31, and that kind of thing. So if we do this, we should get our graph. And you can see right here, these are where our 5 data points lie. So we have one piece of data in our first bin, we have a piece of data here, in this bin, we have 2 pieces of data in these 2 bins, but mostly one piece of data. So what does this tell you about the process we were getting this data from, although it was random? Obviously nothing. You can't really draw a conclusion about this with only 10 data points, because this is it's almost a uniform distribution, right? I mean, there's a bunch of 0s and 1s, and then there's a couple of 2s, but it's pretty much 1 everywhere. So all we're going to do is we're going to increase the number of rows. And the reason we're increasing the number of rows to get more data points is because, as I said before, we're adding across our columns by having axis 1 here. So if I make this 100, I run this, you'll now see that our data is 10 by 100, but our row averages now has 100 data points in it instead of 10. Because again, our data is 100 by 10. And so, it is what we expect. So we plot this again. Now you can see we have a bit more of like a tendency. We can see there's kind of a spike right here in the middle of the graph, a bit above 1. But we have something between 0.7 and we have something around 1.4. But again, it's still not quite enough of a tendency to say any conclusion, and it still definitely is not a bell curve. So we could do 1,000 real quickly, and then just run all 3 of these again. I said run all 3 of them again. There we go. And we can see we have something that's a bit more curve-like now. It's a bit more consistent, but again, still not great. So we're just going to kind of skip to the end here and just make it be the integer form of 1 e to the 6. So that's 100,000 data points, I believe. Let me think for a second. E to the 6 is how many zeros we have. So no, that's 1 million data points. So I run that. I run this. There we go. We now have 1 million data points. And well, we now have 1 million rows, each row containing 10 data points in it, if you think of it that way. But after we take their averages, we only have 1 million data points. And now if we graph those, you can see quite clearly we have a very, very nice looking bell curve. Even though all the way out here, we don't have that many data points, but as we get closer and closer to 1, which is the center of our range, since we added something between 0 and 1 non-inclusive and something between 0 and 1 non-inclusive, we'd expect 1 to about be the average of that. And you can see right here, we average right around 1, and we have a nice smooth bell curve where as we get farther and farther away from 1, we have fewer and fewer data points, almost exponentially. First, not so much, as kind of linear looking, but as we get farther and farther out, you can see the probability tapers off quite quickly. So this does prove that as we increase the number of data points, we get closer and closer to a normal distribution, and so the central limit theorem does hold. This has been a short video, but I appreciate you watching, and in our next one, we're going to get to the derivation of why this actually happens. Why is this normal distribution the shape that data, random data en masse kind of approaches? Again, I appreciate your time. Thank you, and have a good evening.